Let's begin section 4.1 of Anton, and this begins with the definition of a vector space. Now, a vector space is a set V, like Rn, and in fact, Rn will be the main example to think about, with two operations. Addition, which is that if you have two elements of your set V, call them U and V, there's some way to get another element, and that element is denoted U plus V. And the second operation is a multiplication by a scalar. In other words, given a real number R in the set of real numbers, and a vector, well, elements of our vector space are called vectors. So given an element U or a vector U in our vector space V, we have another vector or another element of V denoted RU. Sometimes we say R times U. And these two operations, addition and multiplication by scalars, satisfy a whole bunch of rules, about 10 rules, which you don't have to remember because they're very familiar from the behavior of addition and scalar multiplication in Rn. Namely, so here are 6 of them, or 5 of them. If you have two vectors U and V, well, and you add them, that, again, whatever addition is, that's result is a new vector, or some vector, might not be new, but some vector in V. That's part of even the definition of addition, so this is, number 1 is a bit redundant. Okay, one additional property that's not already established is that U plus V equals V plus U. That's an axiom, or an assumption, or a requirement. So addition is commutative, is another way of saying this property too. Third says addition is associative. In other words, basically the order in which you add things, the order of operations in which you add 3 vectors doesn't matter, or you don't need to use parentheses essentially when you're adding 3 vectors. The fourth requirement is that there is an element or an object or a vector of V. So these 3 words are used interchangeably when talking about elements of a vector space. And that the object or element vector is denoted by a 0 with an arrow above it, and is called the 0 vector. And it's such that when you take the 0 vector, add it to any other vector, you get the same vector back. Concretely, when V is the vector space Rn together with the usual addition and scalar multiplication, this vector 0 is the vector whose components are all 0. Okay, moving on to requirement 5, for every vector in V, there is another vector denoted by putting a negative sign in front of the vector, such that U plus this other negative U vector equals 0 vector, and that negative U plus U equals 0 as well. Axioms 6 through 10 are continued on the next slide. Number 6 says if you've got a scalar R and a vector U, then R times U, the scalar multiplication, is a vector in V. This is just part of the definition of scalar multiplication. I think our book is just being extra careful to list it. So one way that the scalar multiplication interacts with vector addition is that the distributive law holds. Moving on to number 8, here's another version of the distributive law. When you add 2 scalars and multiply the result with a vector, that's basically what you see on the right as in the familiar distributive law. A particular example I've illustrated here, so if you've got 2 scalars like 5 and 3, you add them first, you get 8u. That's required to be the same as 5u plus 3u. Okay, number 9 says this sort of associative law in a sense holds that R1 times the vector R2 times U equals, if you do R1 times RU first within the multiplication of real numbers and then multiply that scalar by U, you get the same result. Here's an example. 3 times the vector 5U is required to be the same thing as 15 times u. And number 10 says the number 1 times u gives back the vector u. This is, again, for all vectors u in V, or all elements of the vector space. Okay, so again, these 10 axioms are fairly, in some sense, familiar, or they hold when you've got the vector space to be the main example of interest, which is Rn. So we've seen vector addition and scalar multiplication on Rn, where n is any positive integer. We can generalize this to what's called r to the omega. This is the W-looking symbol is technically this Greek letter omega. And what r to the omega consists of is sequences, infinite sequences of real numbers, whereas r to the n is a list of, or a sequence of n real numbers. And in both of these two examples, the addition is component-wise, and scalar multiplication means multiply each component by the appropriate scalar. What are components? Each one of these, u1, u2, u3, and so forth, is a component. Another example that seems quite different is if the vector space V as a set is the set of m by n matrices with entries in R, so for some fixed m and n. And then I need to tell you how to add to m by n matrices and how to scalar multiply scalar by a m by n matrix. Okay, so the addition is just the regular way we add to m by n matrices. You add them entry-wise. So for example, the 1, 1 component gets added to the 1, 1 component, and the resulting number is the 1, 1 component of the sum. Okay, and then scalar multiplication involves multiplying each entry by its scalar. So it turns out that this vector space V here is isomorphic to R to the m times n. And we'll see this later, and we'll also see what does isomorphic mean. The symbol here is isomorphic. And so even though this example looks different than the r to the n example, it secretly is of this form. It's r raised to some power, and maybe that's not so surprising because each element of in here, namely an m by n matrix, is the data of m times n number of real numbers. Okay, let's move on to an example that looks completely different from the previous 3 examples we've seen. The previous 3 were somehow all sequences of numbers or some collection of numbers. This one, number 4 here, is as a set. It's denoted, well, f from minus infinity to infinity, and it's a set of functions from whose domain or inputs range from minus infinity to infinity, the real numbers in between here, and the outputs or range or codomain is the set of real numbers. So we call this the space of functions on real numbers. Each element here is a function. Like, what's an example of a function? Well, f of x equals x squared, g of x equals x cubed. So f and g here are 2 examples of functions in this set here. That's what this line here says. F and g are in, or element of. That's how this backwards looking, or this E looking symbol looks like, means. And then this is our notation for our set of functions, whose domain is from minus infinity to infinity. Okay, and then I'm claiming that this is an example of a vector space. Well, to explain that, I have to tell you or define how to add 2 functions and how to take a scalar, like a real number, and multiply a function to get a new function. So the addition is done what's called pointwise. In other words, if I want to add f plus g, and that's going to be a new function. So a function takes a number between minus infinity and infinity as input and gives a real number as output. So if I give some arbitrary number x as input, I have to tell you how to define the value of this function at x. And well, f of x is a real number, and g of x is a specific real number. I mean, they depend on what choices of f of g are. But once you have chosen f and g, they're specific real numbers, and then you can add these two real numbers and get another real number. And so that's how addition is defined. The resulting function is an element of this function space. So for example, if f and g are x squared and x cubed, then the sum function takes x as input and returns x squared plus x cubed. Okay, and then finally, scalar multiplication is, if you give me a real number and a function, I'm going to give you back a new function, and that new function takes x as input and returns. I take the function you've given me, evaluated it at x, and then multiply that real number by the real number r. So for example, if r is 5 and I'm multiplying the function x squared, well, the new function 5f takes x as input and gives back 5 times x squared. Okay, so these are the two operations on this vector space, or on this space, and we have to check that it satisfies all those 10 conditions in order for this set with these two operations to be a vector space. Now, this sort of function space comes up when you're thinking about Fourier analysis, which is a topic we might get to. And the Fourier analysis is about expressing functions in here as a linear combination of certain basis elements stemming from the cosine and sine functions. But for the most part, we won't worry too much about this function space. Most of our vector spaces will be what's called finite dimensional, and those are the ones that are isomorphic to r to the n. So if you're just comfortable with the r to the n vector space, that's just fine. All right, let's do some problems from section 4.1. So this says, determine whether each set with the given operations is a vector space. This is on page 90 of Anton. So problem number 3 says the set of real numbers with the standard operations of addition and multiplication. And the answer here is yes. That's because the set of real numbers is r to the 1. And we haven't checked, but, well, I haven't checked, but people have checked, maybe the book checks carefully, all these 10 axioms hold. Let's move on to something more interesting. Number 4 is the set of all pairs of real numbers of the form x, 0 with the standard operations on R2. And then, so what does the set consist of? It consists of pairs where the second component is always a 0. So -1, 0 is in the set, 0, 0 is in the set, 1.5 is in the set, and so on. And if I plotted what the set looks like on the xy plane, it's basically the x-axis drawn here in magenta. And this does form a vector space. So the answer is yes. Now again, I'm skipping over the details of checking all those 10 axioms satisfy, but we can perhaps one way to see that is this vector space here is isomorphic to r to the first power. Basically, it just means it's the same data as just a single number, and we've seen or assumed that if you have a single number or n numbers where the usual operations of addition component-wise and scalar multiplication on each component, those form or satisfy the axioms of a vector space. Let's go on to maybe some intermediate example like 4.5. So the same as number 4 here, but with the x in x, 0 has to be positive. So here's our first example of something that's not a vector space, maybe though that's in some sense more instructive. So one reason it's not a vector space is 0, 0 is not in the set. And a vector space, one of the axioms was it has to have an element that's the 0 vector that acts as the additive identity. That's a fancy way of saying that when you take that vector or element and add it to any other vector, you get that other vector back. And so this is one reason why this set here, with the first coordinate is greater than 0, the second coordinate is 0, it's not a vector space because it doesn't have the 0 element. Another reason is that it's not closed under scalar multiplication. In other words, if I take -1, the scalar -1, and multiply it by this vector 3, 0, which is in this set, I get something -3, 0, which is not in the set, of ordered pairs where the first component is positive, and so therefore that doesn't satisfy the requirement of the scalar multiplication has to end up back in your set. Problem number 5 here is, again, the same question. Is this set a vector space or not? Now the set is the set of ordered pairs in real R2, ordered pairs of real numbers, such that, so that's what this vertical line is read as, such that the first component or first coordinate is greater than or equal to 0. Now if we graph and then before we graph it, the operations are the usual operations from R2. The addition of two vectors is given by adding component-wise, and then scalar multiplication is by multiplying each component. Okay, so that's the vector space, or the alleged the operations on the space or the set, and then if you graph it, it's the set of these points in magenta here, and this is not a vector space. One reason is that, kind of from the previous example as well, is that a scalar like -1, when we multiply this vector 1, 2, gives a vector that's not in the set, so lands outside the set. Okay, moving on to number 6, the set of elements in Rn that all have the same coordinates, is that a vector space? And the answer is yes. Oh, by the way, the operations are the usual operations of vector addition and scalar multiplication on Rn, and that is a vector space because it, well, you can check all 10 conditions hold, but what it turns out to be is isomorphic to R1, because basically it's the same as the data of a single number that you're adding and multiplying by real numbers. Example 7, or exercise 7, is R3 with the usual multiplication, but scalar multiplication is given by this weird operation where you take the scalar, and to multiply that scalar by the vector xyz, you square the components. Sorry, you square the scalar and then multiply each component by the square. And the question is this strange set with this strange operation, rather, a vector space? And well, you just have to check all 10 axioms, and maybe there's one that doesn't hold, or more than one that doesn't hold, and once you know or find one that doesn't hold, then you know it's not a vector space. Distributive property, and that, it turns out, fails. So for example, well, here's what the distributive property, or one of the distributive properties, says, and let's plug in R1 equals 3, R2 equals 5, then this funny scalar multiplication says that this thing should equal, well, first of all, 3 plus 5 equals 8, and then the strange rule says that to do the scalar multiplication of 8 times this vector, we first square the scalar, so the 8 squared is 64, and then multiply each component by that square. So here's our answer for what 8 times xyz is in this strange land. And then so that's what this left-hand side of this equation here is. And now we have to compare, what about the right-hand side? Well, R1 was 3, so 3 times this vector is what we have to compute, plus 5 times this vector. So R2 is 5. We have to compare, is 64x, 64y, 64z equal to the sum? So we have to first compare this sum. The sum is this. 3 times this vector, in this funny, strange rule that we'll never see again in this book, is 9x, 9y, 9z, and then 5 times xyz is 25x, 25y, 25z. And again, this is only in this example in this book. The rest of the book, 3 times xyz is going to equal 3x, 3y, 3z, because that's the standard operation on Rn that makes it a vector space. Okay, and then when we add these two, the addition rule is the usual rule for vector addition, namely they add component-wise. So 9x plus 25x is the first component, so that's 34x. Similarly, the second and third components are 34y, 34z. And then we have to ask or check, does that equal the left-hand side of the equation, which we computed was 64x, 64y, 64z, And yeah, it's clearly no. 34x is not equal to 64x, so that immediately tells us that these two vectors are not equal. So these two sides of this equation are not equal, and therefore this set of three elements into R3, but with a strange scalar multiplication rule, does not form a vector space. And since it doesn't, that's why we'll never include this operation in the rest of the book. We're interested in vector spaces in linear algebra. Okay, and then let's do one final example. The set of invertible 2x2 matrices with the usual matrix addition and scalar multiplication. And this is not a vector space, since the 0 vector for the matrix addition is the matrix consisting of all zeros, and this is not invertible. Again, what does invertible mean? That means the matrices that have inverses, and there's a very convenient way to check if a square matrix has an inverse. It's if the determinant is non-zero. The determinant of the 0 matrix is 0, and so this this 0 matrix does not have an inverse. It's not invertible. And so this 0 matrix is not an element of our set in question, so the set can't be a vector space.